Welcome to week 11 live session of quantum chemistry of atom and molecules. Today actually I'm re-recording the session because the class we have taken on 8th October I have recorded the session, but due to some audio and video related issues I had to edit it. But after editing, what I felt like it's better to re-record the session anyway. So I am re-recording the session, and the thing we have actually done in previous to previous class was that to the derivation of the perturbation theory, where we have a approximate method where uh, we have introduced the perturbation to a very small amount and find out that what is going to be the first order and second order correction to the energy and the wavelengths wave functions. We have done that, and today our agenda is to solve some numerical problems on that. So I have collected a few numericals from different books like McQuarrie, Simons, Jetili, Atkins, and we will be try to solve them today. I'm very sorry again for uploading the video after maybe 1 or 2 days, because as I told you that I have faced a problem due to the recording. Anyway, those I think on that day nobody actually has joined on the class, but anyway, so it is not a problem. You can watch the video right now, and without wasting much more time, let us delve into the class. And let us start by writing those formula, you can say, or the axioms of what we have understood from the uh, derivation what we have done in the last class. So the first order energy is going to be, if we write it in a bracket fashion, then is the unperturbed wave function complex conjugate in, or you can say unperturbed wave function in the bra, and then your perturbation, which is obviously going to be very small, and then again your unperturbed wave function in the K. Now if I have to write the same thing for first order correction for the wave function, one, and what we have started with that, as the unperturbed wave functions forms a complete set in this Hilbert space or this quantum mechanical space we are talking about. So we can take a linear combination of those unperturbed wave functions to get this the correction in the wave function, right? Which is, so I will write it once. So the linear combination would have been, m could be from 0 to infinity, and this is going to be my coefficient, uh, or you, as I am taking it psi n, so I am writing it cn here. N is denoting that we are doing it for the nth wave function, right? And this is my unperturbed wave function. So we are actually, here the variable is m, right? M is from 0 to infinity. So when we have done the derivation, we have found out a particular condition that obviously m is going to be from 0 to infinity, but another condition we have found out, m cannot be n, and for that particular combination we are going to get this. This is going to be our first order correction to the wave function. So this is nothing but your Cm nth term. Now Enth0 is the energy of the nth state, unperturbed energy state, and Em0 is energy of the unperturbed mth state. So with that we have done also the second order correction to the energy, and that actually looks a little similar because I will tell you it is suppose psi, not psi, we are doing it for the energy, right? Not the function for the energy. So here we use the similar condition. Square of the modulus of this bracket function this psi ml0 is not there. This is going to be your correction term with the energy. And what we have discussed also is that the perturbation we should limit. We limited our discussion to the second order correction to the energy only because as we told you, this is an approximate method. Up to second order correction we can say this approximate method holds. After that it is doing much more calculation. It's not that fruitful as we would have wanted. So those terms are going to be even smaller than these correction terms in the second order correction, right? So anyway, and uh, so that won't be that fruitful, to be honest. Anyway, now the next discussion, what we are going to do, we are going to solve some numerical problems, obviously. But before starting those problems, let me mention that the main thing we are going to focus on solving this question, as we have obviously seen for the other numerical problem solving for the quantum mechanics also, that we are going to rely on the integration very much. So one have to be a little efficient on the integration. Even I make mistake. I'm not sure, but if while doing the next set of solutions, you may see that I am also fumbling in some places, but it's okay. Hey, we should solve as many problem as we can so that our fear of doing this integration by parts or integration should go away, and we can do a good job on this solving problem. And we also may have to play with, obviously we are working in the physical chemistry domain, so we need to be very careful about the units we are working on. Anyway, before wasting any more time, let us go to the first question. Actually this question, actually I guess, was in the assignment, but I kept it here so that we start with a problem, integration problem, which is going to be easier. So the question was that a particle of mass m is confined in a finite potential with boundary conditions. V of x is 0 when it is inside the box. Obviously x is from 0 to L, and infinity otherwise. Similar, the first order problem, right? The box in a 1D box kind of a problem, right? Where your potential is infinite, you have two infinite well at two sides, and where the particle resides, the potential energy of the particle is zero. Now the question says the particle is subject to the perturbation W is equal to beta x within the box, where beta is a very small constant. Here your beta works like a lambda kind of thing, what we have discussed in the previous class. So this is beta x is going to be your perturbation. So then the first order correction to the energy, what will be? Obviously the first order correction, if when we write in a bracket notation, as I showed you, it is going to be your unperturbed wave function, your perturbation, what is written W here. Obviously your W is beta x, where beta is very small, so I can write it like this. And another thing, what is that, your, if you remember the particle in a 1D box, what is the unperturbed wave functions look like, as it is from 0 to L, we know the wave function, that is root 2 by L is a sine function, sine n pi x by L, where n can be from 1 to 3, not 0, right? It could be any positive integer. Now for this particular case, what do we have? If we write it in maybe in terms of the bracket notation, it is going to from 0 to L. First it is going to have this 2 by L sine n pi x by L. If I have to take a complex conjugate anyway, that doesn't really matter because they don't have any uh, what should I say, they don't have a imaginary term, so that doesn't really matter. And then the next is your beta x, your thing, and then is again your this sine n by x by L dx. So we will, what we will do, we will first take out all the like constant out like beta, then divided by L. You, I know you are thinking I missed 2, but I am not actually. I am, what I am writing, I am writing a 2 here, 2 sine square n pi x by L dx. Okay, now you have to use this trigonometric relation many a time in this course, which is cos 2 theta is actually cos square theta minus sine square theta. Now cos square theta can be written as 1 minus sine square theta, right? And this is also sine square theta, so you get 1 minus 2 sine square theta. And for that particularly you get 2 sine square theta as 1 minus cos 2 theta. So actually we have done this because our integration is actually going to be easier if we do it like this, x 1 minus cos 2n pi x by L dx. Obviously you can expand it, beta by L 0 to L, write a third bracket x dx, and your another integration 0 to L x cos 2n pi x by L dx. Now this you can do it easily, but for this part you have to do a integration by parts. So let us first do that in a different color. Maybe here we are doing it, x cos 2n pi x by L dx. So integration by parts. So here what we have to do, I will take x outside and integration of cos 2n pi x by L dx, and then I'm going to have minus, then integration, then I'm going to have a second bracket. Here I am going to write d of d dx of x Then I am going to have an integration of same cos 2n pi x by dx. Sorry, my mistake. 2 cos pi n by l dx, and obviously a dx here because we have double integration here. So from the first part will yield us x. Now we have the constant that is going to be L by 2n pi, right? What else? The integration of cos actually leads to sine function, sine 2n pi x by L. What does the below part is going to give us? Dx by dx is going to be 1. Now as we have done the integration already once here, we know what we are going to get here, that is L by 2n pi integration of sine 2n pi x by L dx, right? And here we are going to get, and I will try to write it in a fashion that we can cover the part, 2n pi sine 2n pi x by L minus L by 2n pi square of that, because we are going to get the same term again as we are doing the integration here, and we are doing an integration of sine function that would lead to plus cos, sorry, minus cos. So minus and minus will become plus here, and a cos 2n pi x by L. That is what we are going to get here. So I will just put the value here, that beta by L inside the box, and it is going to get me x square by 2 for this, and it is my L to 0. And for this part we are going to get x L by 2n pi sine 2n pi x by L plus L by 2n pi square of that, and cos 2n pi x by L, and also the limit goes from L to 0, and we have the third bracket here. Okay, now we are going to the next page and solve the rest of the part. So what we have till now is that we are solving for the first order correction, and we have beta by L. Then we had what here, x square by 2, and the limit is from L to 0 to L, so it is going to be L square by 2 minus 0 square by 2, leading to here. This part is done. What about this integration? Here you put L first, so it is going to become L square by 2n pi sine 2n pi L by L going to cancel, so it is going to be a 2n pi, right? What it is going to be, L square by L by 2n pi whole square cos 2n pi LL, again going to cut, and then when you put 0 here, so 0 into L is going to be, the whole function is going to be 0 anyway, sine 0 is also going to be sine 0, it is 0, so we don't have to think about this part is going to be 0, and when we are going to put 0 for x here, so that is going to be cos 0, which is 1, so we will put the values one by one. So this is one part is done, and we now have the L square by 2n pi sine 2n pi is left. Then we have plus L by 2n pi whole square. Then we have the same thing, cos 2n pi. Then we have, I told you, we are going to have 0 for the third term, and this term we are going to have L by 2n pi square cos 0. Cos 0 is 1. Like this. So we are going to have beta by L. First we have L square by 2 from here, and then we have L square by 2n pi sin 2n pi. Now see, we know what sin n pi is. Sin n pi is always going to be 0 whatever value of n it is, from 1 to 2 to 3, anything. So any value of 2n pi also sin is going to be 0, but explicitly I will write it here, L square by 2n pi into 0 plus L by 2n pi cos 2n pi. Cos 2n pi is, if it was n pi, cos n pi, then it could have been plus 1 or minus 1, but as it is 2n pi, so your 2n is a even number always, so 2n pi, cos 2n pi always going to lead you 1. So this is cos 2n pi value is always going to be 1 for any value of n. Now third term was 0 anyway, and this is your cos 2n pi square. Now if you see, this term is going to be 0, and this term and this term are going to cancel each other. So actually we are going to live with dl square by 2, that is beta L by 2. So let us see if this correction is given or not. Yes, if you see this B, this is going to be our correct option. Okay, now I hope from this solution itself we made ourselves clear that we are going to do integration mathematics only in this, and we are going to need the help of trigonometric function very well, huh? But for, as a spoiler, I will tell you, I have a question where to get the first order correction we don't have to do the integration. I'll show you how, but let us see how the class unfolds. Now we have a question again here, and this question is actually from JTL. So the question says that using the first order perturbation theory, calculate the energy of the nth excited state for a spinless particle of mass m moving in an infinite potential well of length 2l with its wall at x is equal to 0 and x is equal to 2l, such that its potential energy is 0 when it is inside the box and infinity when it is otherwise. And then it is modified by one perturbation that is known as given as Vpx is lambda v naught sin pi x by 2l. So see, we know what we want to get. We want to get the first order correction to the energy. What is that? In bracket notation, this is what we want to solve for. Okay, what are the things we know? We know the perturbation is given by lambda v naught sin pi x by 2l. What else we know? See, usually we work for a particle in a box where the potential walls are at x is equal to 0 to L, and that time we got our wave function as root 2 by L sin n pi x by L. But in this particular case, the box has a length of 2L. So your potential walls are at 2L distance, x is equal to 0 and x is equal to 2L. So your wave function is also going to modify it. So it would be like this, and if I write it here, it would be 1 over L sine n pi x by 2L. Okay, so these are the things we know, and obviously these are the, I have missed it once, so this is here zeroth unperturbed wave function, right? So that we need to work on. So let us write it in the integration from 0 to 2L, right? Now our boundary has a little difference. First part have 1 over L sine n pi x by 2L, complex conjugate of that, actually, which is nothing because there are no imaginary term. Now we are multiplying with our perturbation lambda v0. Interestingly, the perturbation also is a sinusoidal function, which is going to be interesting, right? And again, the our unperturbed wave function, and dx. As a first step, we will take all the constants outside, right? What we are left with? We are left with 3 sine functions, out of which one is sine pi x by 2L and another is another 2, but I can write it as a sine square function n pi x by 2L, right, dx. We know what we are going to do, right? Whenever you see the sine square function, you know, I guess from now on you know what you have to do. You can take a 2 in the denominator, you can multiply it here, right? So now it has become 2 sine square n pi x. We are in a familiar territory of the trigonometric functions, right? So we are going to get lambda v0 by 2L 0 to L sine pi x by 2L, and we are going to have 1 minus cos 2n pi x by 2L and dx. So we can write it also like this, lambda v0 by 2L, can break it down into, see, I have made a mistake here, 2L, right, 0 to 2L sine pi x by 2L dx, and another we will have 0 to 2L sine pi x by 12 cos 2n pi x by 2 and dx, obviously a whole bracket. See, this sine integration of this sine function is going to be very easy, but as you can see here we have two trigonometric function, so it's not going to be a very easy one, right? So what we will do is, if you we are going to take help of trigonometry again. So how we will do it? I am so we will first let us solve this integration first, right? Sine pi x by 2L into multiply by cos 2n pi x by 2L. So let me do it. I will do it in a different color. So first we will going to solve for 0 to 2L sine pi x by 2L cos n pi x by 2L dx. Now if you remember, that 2 sine A cos B, we can represent it as suppose sine A cos B minus sine B cos A plus sine A cos B plus, let us take the plus one first, cos A sin B, same thing. I am just doing it the usual way, and we have to take a minus combination here, cos A sin B. So if you see these first two are sin A plus B, and the third, fourth are sin A minus B. So actually a product of sine and cos function, we can write it in a sum of two sine functions. So for that we need to take 1 by 2 here and multiply it by 2 here, right? So 1 by 2, 0 to L. Now it is going to become sine pi x by 12 plus n pi x by 12. I am making a mistake. It is 2n pi x by L, right? Yes, 2n pi x by 12, and we are going to have another option, that is sine pi x by 12 minus 2n pi x by 12, and this was a different part. Now 1 over 2, 0 to 12, my mistake. So we can write it sine, the first part as sine 2n plus 1 pi x by 12 plus sine 1 minus 2n pi x by 12, and obviously we can write it in this fashion, 0 to 12 sine 2n plus 1 pi x by 12, and I will take minus because I want to make it look like sorry, I should have taken first bracket here for consistency. So one can actually write sine minus b as minus sine b, right? So I am taking this combination, so it is going to be 2n minus 1 pi x by 2. This is just simple trigonometric thing. The main thing was here, that how you are going to solve this. We can make it in a sum of two sine functions. Half 0 to 2, 0 to 12, but let us not write. Now if you do a integration of sine, obviously you are going to get minus cos, then the same thing, 2n plus 1 pi x by 2l, obviously multiplied by this 2l divided by 2n plus 1 pi, and from this section you are going to get a minus cos function, right? But minus minus it will be plus cos 2n minus 1 pi x by 12 multiplied by 2x by 2n minus 1 pi, and obviously you are going to have this limit from 0 to 12. So we'll put the values of x here and try to look at that what we are going to get. Obviously we have 12 here and we have 2 here, so we can actually cancel them out at the beginning. So we can write it. So first is minus cos 2n plus 1 pi, right? Because x, when you put it 12, so 12 and 12 is going to cut, and your constant term is 2n plus 1 pi, right? Then this cos, same thing is going to happen, 2n minus 1, then pi is going to be, because x and 12 is going to cut, and you are left with your 2n minus 1 pi here. Now when you put 0 here, what you are going to get? Minus cos 0, right? Multiply by your L by 2n plus 1 pi. What about the last part? For that also you are going to get cos 0 multiplied by L over 2n minus 1 pi, and the bracket is closed. What is the value of cos 2n plus 1 pi? So you can see this is always going to be a odd number, 2n plus 1. So it is something like cos m pi is always going to be minus 1 when m is odd. Okay. Similarly, 2n minus 1, this is always going to be odd, right? So this, for these two cases, we are always going to have minus 1, the cos functions, what I am trying to say. Okay. So let us write the value. So minus 1 and minus, that is going to be plus 1, and multiplied by your L 2n plus 1 pi, plus, not plus, now it is plus and minus, it would be minus L 2n minus 1 pi, then you have cos 0 is 1, so L by 2n plus 1 pi, right? And we have minus L by 2n minus 1 pi. Okay. So from here what we can see is that, let me first check if I am making any, I am making one mistake here. As you can see, this is minus cos, right? So up to this two part was correct, then here I have to take minus of minus cos thing, so it would have been plus. So see it would have been cos 0, because here it is minus, so, and we are putting the value of 0, now the lower term, so it will be minus of minus cos those, so it would have been plus, and this part is fine, so here it is also going to be plus. So what we are going to get is, from this integration, is 2 by 2n plus 1 pi actually 2l this one and the third term, 2l by 2n plus 1 pi and minus 2n minus 1 pi. So this is what we are going from this second integration, this one. So we will put the value of that into the our equation. So maybe from here onwards, so we are calculating the first order correction to the energy, for which we got the expression lambda V0 by 2L, integration from 0 to 2L sine pi x by 2L dx, and integration here minus 0 to 2L sine pi x by 2L multiplied by cos 2n pi x by 2L dx, bracket, third bracket close. And what we have found out that we have this integration, this part solved, and so this part what we got is minus 2L by 2n plus 1 pi, right, and minus 2L by 2n minus 1 pi, right. And from the first part we are going to get a cos function, right, because integration minus cos of pi x by 2L obviously multiplied by this constant term 12 by pi, and obviously it would also have a limit from 0 to 12 lambda v0 by 12. So cos, when we put 12 in place of x, it is going to be minus cos pi multiplied by 12 by pi obviously, and in another case it is going to be minus minus plus cos 0 into 12 by pi, right. And this we know we are having 12 by 2n plus 1 pi minus minus plus 12 by 2n minus 1 pi. So actually we can cut this 12 from every cases. What I am trying to say is we can 12, this 12 will go, this will go, this will go, this will go. This is going to help us in the thing that lambda v0. Now minus cos pi is minus 1, so minus cos pi is going to be plus 1. So it is plus 1 over pi plus 1 over pi minus 1 over 2n plus 1 pi plus 1 over 2n minus 1 pi. Again we can take the pi outside as common in the denominator. So we have 2 minus 1 by 2n plus 1, and we have 1 over 2n minus 1. We need to simplify this. When we simplify this, we are going to get 2n plus 1, 2n minus 1 at the numerator also, and it is going to be 2n plus 1, 2n minus 1 in the denominator, then minus 2n minus 1 and plus 2n plus 1, and overall we are going to get lambda v0 by pi 2 into 4n square minus 1. Here it is going to be 2n plus 1 plus 2n plus 1. And it is lambda v0 by pi 8n square minus 2, and this minus 2 and plus 2 is gone, plus 2 is remaining, n square minus 1, so this is nothing but going to be 8 n square lambda v0 divided by 4n square minus 1 pi. So this is going to be your first order correction to the nth energy, nth energy nth state, energy of the nth state. So let me write it down, that first order correction to the nth state, to the, let me write, to the energy of the nth state in this particular quantum mechanical system is going to be 8n square lambda v naught 4n square minus 1 pi, and remember n can only start from 1 to any positive integer, because this is a particle in a 1D works problem, and we know from the solution of the quantum number cannot be 0, right? Okay, so now we got some idea here. Now let us go to the another problem from ZTLE, which is interesting because in this problem you can see what there is a matrix is given. So the question says, consider the system whose Hamiltonian is given by this uh, matrix kind of thing. E Hamiltonian is equal to E0, then there is a 4 by 4 matrix, 4 column, 4 rows and 4 columns, started with 1 plus lambda, then in the second row second column 8, third row third column 3, third fourth row third column minus 2 lambda, third row fourth column is minus 2 lambda, fourth column fourth row is 7, and the other terms are 0. And it is also given that lambda is very less than 1, very small. So actually part Hamiltonian that is given, it is actually not your uh, unperturbed Hamiltonian. This is a perturbed Hamiltonian, and it is also said that by decomposing this Hamiltonian into H is equal to H zeroth plus H perturbation. So we need to do three things here. One, that we need to find the actual zeroth order Hamiltonian. Zeroth order means unperturbed Hamiltonian. The perturbation part of the Hamiltonian, and then we need to understand what are the eigenstates are related to this unperturbed Hamiltonian and what are the eigenvalues are. Okay, so whenever we have this kind of problem, this matrix kind of problem, what we have to do is that we need to break it down into to be honest, in some way or the other, we have to see if there is we can make a sum of a diagonal and off diagonal terms. So as you can see, we may able to break it down into a diagonal matrix and a non-diagonal matrix, sum of two. Let us see how can we do that. So E0 1 plus lambda 0 8 0 0 So you can write it in terms of two matrix where it is 1 0 0 0 0 0 0 8 0 0 0 3 0 0 0 7. So this is a diagonal matrix and a matrix where there are out diagonal terms are also present. And this is our, so you could break it down into two matrix, one diagonal and another consist of diagonal terms. So this is actually your unperturbed Hamiltonian, and this is your perturbation. Okay, and how can we write this part? We can take the lambda outside, right? And lambda is very smaller than 1. So the first part is done, that we have decomposed this Hamiltonian into the unperturbed Hamiltonian and the perturbation. Now, so this is a 4 by 4 matrix, the unperturbed Hamiltonian. So it will work on the eigen states or the eigen functions, and it will lead to some eigen values. So the eigen states have to be of the matrix have to be of the order of 4 into 1, right? Then only it should have, at least it should contain 4 columns, sorry, 4 rows. So this is suppose one part. Now let me define the eigenstates. Eigenstates are going to be, suppose, psi a, the first one, that is your 1 0 0 0, psi b, here I have made a mistake, 0 0 1 0, psi b is so these are your eigenstates, and these as they are your eigenstates. So when you apply the unperturbed Hamiltonian onto these, what I am trying to say, when you apply this, so unperturbed Hamiltonian here is denoted by H naught. I will also write that. So when you operate H naught on psi A, you are supposed to get back your energy unperturbed of the eighth state and your wave function as back eigenfunction, right? Something like that. Also for this case also, right? So you are going to get the unperturbed energy for the bth state, and obviously you are going to get back your unperturbed wave function. So I can also write it like this, the unperturbed to for this also going to have the energy of the unperturbed state. Okay, so we will apply this to get the eigenvalues. Okay, so in the next page maybe we can do that. So your H naught is defined already, right? It is A0 1 0. So this is your H naught, and your psi A is 1 0 0. Okay, when you then apply your H naught on psi A naught, you are going to get the matrix multiplication between a 4 into 4 matrix and a 4 into 1 matrix. And you will get E0 is obviously outside. So what you are going to get is, so you are going to multiply each of the row term with each of the column term as a row element, and you are going to see you are going to have only 1 at the top and the rest are going to be 0. So obviously you are going back your E0 is high, so your E naught is okay. Now next, when you are operating H0 on psi V naught, the matrix multiplication also between 4 into 4, this. So obviously you are going to get only the second column, right, which is a 8, can be write as 8 can be taken outside, 8 not 0 1 0 0, 8 not psi 0 dot. So one button is. So when you apply your unperturbed function Hamiltonian on the unperturbed uh, cth state, this case, similarly you are going to get this. Nothing, but I will do a step jump here. I will not maybe. So here this is actually size not. So your unperturbed energy is 3. What about the bth state? I hope you already got the answer to yourself, right? You just need to know how matrix multiplication works, and that will. Interestingly, if I now going to show you the energies, the state, they are a little different than what we are usually getting. I'm just highlighting the values we got. So what I was telling, if you see the scale, energy scale here, and these are your states. Actually, this is your A. This is your actually bth state. By nomenclature, you should not see. You have to go with the energy value, right? Energy to this is 80 naught, 70 naught, and this is 3 naught. This is naught, right? So I hope you got the understanding what we are trying to do here, right? So if you are getting a matrix kind of thing, then you need to break it down into a sum of two matrix, where one could be the off diagonal that could have the parts, and one should have the only the diagonal matrix, and that would be your unperturbed Hamiltonian. And from then what we have done, we have found out if it is a 4 into 4 matrix, so how what the eigen state should look like. And then we use the normal eigenvalue equation to and matrix multiplication methods to get the eigenvalues related to the eigenstates. Okay. Now the next question is also interesting. This is, I guess, from GTD. The earlier questions were from earlier questions also from GTD. I'm not exactly remembering, but this question. So this is the question where I was talking that to get the first order perturbation, I don't really have to do the integration. But before that, let us read the question very carefully, as it is a very big question, right? So if we need to read the question carefully. So the question states that a particle of charge q and mass m, which is moving in a one-dimensional harmonic potential of frequency omega, is subject to a weak electric field epsilon in the x direction. A particle of charge q and mass m is moving on a one-dimensional harmonic potential of frequency omega, is subject to a weak electrical field epsilon in the x direction. First of all, other terms we should look at, that this is a one-dimensional harmonic potential. So we are dealing with something related to 1D simple harmonic oscillator kind of thing. One thing is for sure. So the previous problems were related to 1D box, right? Now we are dealing with a system which is a one-dimensional harmonic oscillator kind of thing, and your particle has a mass m but also a charge q, and the frequency, moving frequency is omega, and it is subject to a weak electric field epsilon in x direction. So this weak electric field epsilon in the x direction is actually its perturbation, right? So a weak electric field in the x direction is your perturbation, and this is your system. Okay, let me highlight it maybe into different colors. So I am highlighting which part to look at, right? Because this is a very big question. So what are the things we should look at first? That obviously we need to do some integration of some mathematics, but before that, what are those mathematics are going to be, to understand that, or what are the formulas we will going to require for that, I am showing you the steps. So the first question is find the exact expression of energy. One thing. So first of all, one-dimensional harmonic potential. So your energy, energy of the nth state of the unperturbed state is going to be n plus half h cut omega, right? As omega is frequency given, right? Omega is angular frequency, something like that. One thing is that you know what is the unperturbed energy, where n can be from 0, 1, 2, right? Anything. And as your perturbation is a weak electric field in the x direction, so that is going to your perturbation, and for that you are going to have some, so your En is going to have some, obviously the unperturbed, plus some E1, En, maybe I write it's K or something, it could be 1 or 2. So this is your correction coming due to perturbation. Okay. Now see what are the things given. Something is given, that your Hamiltonian is given. Hamiltonian is minus h cut a square by 2m d square dx square plus half m omega square x square plus q psi of x, like that. One thing is that, and some other things are given which we are not going to require now, but for the next part. You know that this part, let me erase, I will highlight the part. So this is your perturbation, because you know that this color is not good. The unperturbed Hamiltonian. The first part is your kinetic energy in the x direction, and then this is your potential energy, right? And this is your perturbation. So obviously, if you want to see the correction term, you need to, first order correction is all you know that it is given by your psi n 0, then your, obviously directly write qex here, that is your perturbation is going to be like this. And if you want to look at your second order correction, so then it is something m is equal to 0, which is not is equal to n from infinity, m can be from 0 to infinity, then modulus square of psi n 0 qex, then psi n, so psi m 0, modulus square energy of the unperturbed nth state and energy of the unperturbed mth state. These are the two things, and for the both of the things we need to do some integration. But what are the other way? So as I told you, in this problem we are not going to do the integration, and for a beginner it would seems to be surprising, because how do I know that? How do we are going to know that for this problem we are not going to do the integration? Because to be 12, the answer might be lame, that I knew the solution, that's why I'm doing it. But see, if you are going to do a integration method, you want to go through this thing by doing integration, then obviously what you wanted to know, you want to know the unperturbed wave functions for nth and mth state, first of all that. And you remember that they carry a Hermite polynomial and some other functions, right? And if it is not given in the question, see, in the given question the wave functions are not given, and I believe at this point of time you also don't remember the exact wave function, right? You know the wave function of particle in a box, because that is a sinusoidal function, and uh, that was easy. You might remember some parts of the wave functions from the you may not remember the radial or the angular part, but you may remember the phi part of the theta part, phi part of the solution of the hydrogen atom problem. What I am trying to say, remembering is not never an option, and these wave functions are not given here. So we wanted to do something so that by some way we don't have to do the integration, because we don't know the wave function. Here the another way to do is, we need to change the variable x to y in such a manner so that dimensionalities are not affected. By how? That we are going to introduce a dimension y which is related to the x by this. Y is equals to x plus q multiplied by epsilon divided by m omega square. I told you that we are changing the variable such a way that we are not, we are making the dimension same. So this is unit of y is, or dimension is length for x. So how do we make sure that this part is also x or this part is also x? So you remember the unit of charge is coulomb. The unit of epsilon, the electric field, is volt meter inverse. The unit for mass is kg. Omega square is your square of the angular frequency, which is going to have 2 pi square. Nu square is frequency, that is hertz, or second minus 2 here is going to be. Coulomb into volt is joule, so it is joule meter inverse. In terms of 2 pi and all, one can say that 2 pi radian is going to be, but radian is not a proper, or I should say the basic units, so we can ignore that. Kg into second minus 2. Joule is Newton meter, so obviously it is Newton meter into meter inverse kg second minus 2. Newton is going to be there. Newton is unit of force. Force is mass into acceleration, right? By second law of Newton, motions of law. Kg meter second minus 2. This is acceleration, this is mass. Now in denominator already kg and minus 2 was there. So if you cut that, you are remain with meter. So you are all okay with this assumption. So I am telling you, this is our assumption. We are introducing y such a way that it is x plus qe by m omega square. What it going to lead? It is going to lead as, see first, x is going to be minus epsilon omega square. Then your dx is going to be equal to dy. In other way, d by dx is going to be d by dy, and d2 dx square is going to be d2 dy square. ठीक है? Now this is our Hamiltonian. I will write the Hamiltonian again. So that is minus h cut square by 2m d2 dx square plus half m omega square x square plus u epsilon x. Now we will replace x with y. So I showed you this is already y square. Now half m omega square, and this is going to be y minus q epsilon by m omega square plus q x instead of x. So see, the y dimension is arbitrary, right? That is our, so we are defining y as x plus q epsilon plus divided by m omega square. Don't think this is a something meaningful. So we are particularly taking that QE by m omega square because we already know what, if we take that particular value, then our calculation is going to be easier in the future steps. As somebody has already done, that is why we already know. Means we are actually using the knowledge of our forefathers, or you can say our predecessors, what we have, they have already done this. It's not like that we know it from the beginning. So if we break it down, so we are going to see that we can cancel a few things from it. First, these are going to cancel, and second, this is half q epsilon square by m omega square, and this is minus q, actually I have written it, it is wrong, q square. So ultimately your Hamiltonian now looks like the way we have defined y, we are getting this as our perturbation, the last term. I'll highlight. This part, earlier what we said is, this part, see, when it was in terms of x, then also it was, now it is in terms of y, you can say. Huh? So this is your unperturbed. Hamiltonian in y, right? Now the interesting bit is that see this, earlier you had a perturbation does not contain y. So if we had to do the first order correction or any order correction, suppose how we do a kth order nth order correction to kth state, that is we write something like this, right? Psi k nth. Now this is your perturbation. So this was one of our assignment problems, right? From the week 7, what I remember. If you see, so this perturbation is now not dependent on the variable. I should, or easier terms, it is a constant. So every time it will come minus half q square epsilon square by m omega square. It would come outside. Obviously this is your something like that is going to come out, and that's why it is going to constant, right? So in other terms, what I am trying to say, let me write it here. So your energy expression is, as I told you earlier, it is going to have some form of this. So you know n plus half h cut omega was your unperturbed energy of the nth state, and now it is your perturbation is going to be this constant. So q square epsilon square by m omega square. That is your final energy expression. So this is the answer to the first part. The second part actually states that calculate the first non-zero correction to the energy, treating q epsilon x as the perturbation and compare it with the exact result obtained in 1. Now suppose we had to do the integration, like suppose this is a first order correction. I told you. But we remember that if psi n 0 is going to be symmetric, right, here in integration form it is minus infinity to plus infinity, right? You have u epsilon outside as their constant. You have psi n 0 and you have x, you have psi n 0 dx. Now if your this psi n 0 is symmetric, then your obviously your modulus square of this is going to also symmetric. If psi n 0 is antisymmetric, then also it is going to this psi n modulus square is going to be symmetric, because antisymmetric into antisymmetric is going to be symmetric. But your x is always antisymmetric, hence the integrand I is always antisymmetric. As we are working or integrating under a symmetric boundary minus infinity to plus infinity, the integral will always be 0. Example, a sinusoidal curve 0, pi by 2, pi, 3 pi by 2, 2 pi. See, in this area your wave function is antisymmetric, or what I'm trying to say, your if I have to get the area under the curve for this, you see, under a symmetric boundary, so you can see your wave function is symmetric under this, right? Wave function is symmetric means like this, and your by not this is not the way should be discussed. The other way could have been minus infinity to plus infinity I dx is only going to be equal to, so I of x plus infinity, I of minus x is going to be I of x dx. That means your integrand is symmetric here. The other way what I was discussing was, I guess, that much mathematics stuff. So the way I was discussing is, suppose this is the function and this is the symmetrical boundary, okay, and your function is antisymmetric as you can see. So at this boundary, if you have to get the area under the curve, they are going to cancel each other, right? So that is, you are going to get the area under the curve is 0, which is your integral. Integrand is antisymmetric, but you're working under a symmetric boundary, so your integral is going to be 0. which means your first order correction is always going to be for this kind of thing. What about first order correction? Are always going to be 0. What about, so it is non-zero, so we are shifting to second order correction. How does this define mathematically? Summation m from 0 to infinity not equals to n, then modulus of psi m 0, you, here it is qex, now psi m 0 square of the modulus energy of the unpart of energy of the nth state minus unpart of energy of the nth state. Now here could be m could be from 0 to infinity, not n, but we can have the situation where if I expand it some terms, then have a situation where n plus 1 why did I took these particular two terms? Because if you see the question, there are two integrals are given, psi n plus 1 x n and psi n minus 1 x n. So those integrals are given, so I don't have to remember, don't have to know the other wave functions. And there could be other terms also, but let us omitting the other terms in en2. We are getting, obviously we are going to get q square epsilon square outside. We now have modulus square of psi n plus 1 0 x psi n. Right, one this term, and then we have when we are ignoring the other terms, because we want to get the non-zero part only. Even it have some non-zero part, we are okay with that. And there could be other terms which can be equals to 0. Maximum, what can happen? The other terms can be equated to 0 or any other terms. So these terms should not be 0. If other terms are 0 and these terms, with the other terms which we are omitting, those are 0, and these two terms are 0, then it is also going to be a 0, right? The overall en2 is going to be 0. But suppose the other terms are 0 and this is going to be non-zero, then the second order correction is going to be non-zero for this part. So that is why we are omitting the other terms. We don't have to think about those. Let us see that if these yield a non-zero value or not. So that is the philosophy behind omitting the other parts and looking only at these things. And it is given that your psi n plus 1 it has some values such as and there are some, if you think about the energy states, if this is your psi n 0, obviously when we look at the energy going upwards, psi n plus 1 0 psi n minus 1 0. The energy of this state is, if you remember, this is in a harmonic potential wall, it is n plus 1, n plus half. What is this going to be? H omega n plus 3 by 2. What is this? H omega n minus half. So the gap between them is going to be h omega in both directions. H cut omega. And let us see what are these values given. One is root n plus 1 into root h cut 2 mw. M. The first part is going to generate n plus 1 h cut by 2m omega and en not minus, see this the difference, the energy this is minus this, so it is a minus quantity h cut omega, but in this case it is having h cut by 2 omega and this is plus h cut omega. So we are going to get some n plus 1, h cut is going to cancel, it is going to be 2m omega square but a minus, and it is going to be n by 2m omega square, so it is q square epsilon square n minus n minus 1 2m omega square, which is half q square epsilon square m omega square. Now see, the terms we omitted in En2 are non-zero, suppose, and plus half q square epsilon q by m omega square. So that would also lead a non-zero correction, right? And if the terms we omitted in En2 are 0 plus these two terms, q square epsilon square by m omega square, then also it is going to a non-zero correction, right? So overall the second order correction energy yields a non-zero correction. Okay, so that is the first part of the second question, is stating that calculate the first non-zero correction to the energy, and that is going to be your second order terms, right? Second order correction, and compare it with the exact result obtained in one. Okay, so first of all, in a exact energy expression is the energy for this, and this is the perturbation. And if you check here, the here I will write maybe in some different colors so that you will find it. The perturbation in the exact energy expression is same is same that of the first, or not the first, but the second order correction. That is exactly same, minus half. I should not, I have written a little, I have done a little mistake here. I forget the minus term. Anyway, that doesn't change the answer. So that is the same thing as that of your perturbation. So with this problem, this is the first problem we have done for the one-dimensional harmonic oscillator for the perturbation theory. I know this question is a little bit tough, to be honest, but it does clear some of the understanding that how with changing only the dimensionalities, or how we can introduce a different dimension to solve a problem easily. One thing that, and obviously the idea of this integration, that first order correction is going to be zero under a symmetric boundary condition for an asymmetric integral, and these corrections are going to be, second order corrections are going to be same of that of the exact energy expression we got. With that, let us so that problem was, I understand that was quite a heavy problem, but now let us solve a quite a easy problem, so that this is going to be clear. See, this is again a first order. See, the question is from Atkins. A small step in the potential energy is introduced into one-dimensional square wave problem. Okay, write a general expression of the first order correction to the energy state E01. Obviously, see, it should not be E0, it should have been E1, right? Because in perturbation theory, sorry, in particle in a box, there is nothing called E01, right? Okay. Now, let me write. So, what is the wave function unperturbed? That is obviously root 2 by L sine n by x by L. How much is the perturbation? That is epsilon. Where it is working, epsilon and 0. Where it is epsilon, epsilon is working when your x is L by 2 minus a by 2 to L by 2 plus a by 2, and elsewhere inside the box, right? So this is your perturbation, or I should write something like that. Now your perturbation then is going to be, suppose I am writing a general thing, right? So it is going to be I naught epsilon. See, this is L by L minus A by 2, and this is L plus A by 2. From where the perturbation is there. That's why I have written it like this. So one can write it like this also. You can use the eraser. Okay. So here it is L minus A by 2 to L plus A by 2. This is not 0 to L. Only the perturbation is working in this condition. So we are going to measure it here. So it is root 2 by L sine n pi x by L. Your complex conjugate of that. Your epsilon is constant, so it will come out. Then it is root 2 by L and again sine n pi x by L dx. And it is 2 by 2 epsilon by L is coming outside. It is L minus A by 2 to L plus A by 2. We have sine square n pi x by L dx. So obviously we will take these two inside to our familiar friend, so that we will get epsilon by L, L minus A by 2 to L plus A by 2, 1 minus cos 2n pi x by L dx, right? So we have epsilon by L, L minus A by 2, L plus A by 2 dx minus epsilon by L, L minus A by 2, L plus A by 2 cos 2n pi x by L. So first part gives us L plus A by 2 minus L minus A by 2. Second part gives us L by 2n pi. Integration of cos is sin n pi 2n pi x by L. L plus A by 2 to L minus A by 2. First part leads to epsilon by L. L plus A minus L plus A. Then this leads to epsilon by L. L got cancelled. Here also L got cancelled. this 2 and this 2 is gone, so I should not write these 2 here. Let me write it once so that no one get confused. A epsilon 2a by 2 is going to be this. So here we put epsilon by 2 by sine n pi plus n pi a by n minus sine n pi minus n by a by a. So now we have sine a plus b minus sine a minus b, and that is actually nothing but sine a cos b plus cos a sin b minus sin a sin b minus plus cos a sin b. So actually it is 2 cos a sin b. A epsilon by L epsilon by 2n pi divided by 2 into cos A is n pi sin is n pi a by n. Sin n pi depends which n we are going to take. So two are going to cut. Epsilon by n pi cos n pi to sin n pi a by L. So this is the general expression for send to the nth state and to the energy of nth state. Now this is the first part. Now evaluate the correction for given that A is L by 10. So the blip, what does that mean? That the blip in the potential occupies the central 10% of the well with n equals to 1. So what does the energy correction be? This is your energy correction. I will write it once here. That A epsilon by L first, that then minus epsilon by n pi multiplied by cos n pi multiplied by sin n pi a by L. by 10, then what is going to be E1 1. N is also 1. So L by 10 into epsilon by L minus epsilon by cos pi into sin pi L by 10 by L. So it is epsilon by 10 minus epsilon by pi. Cos pi is minus 1, so it is going to be like this. It's in pi by 10. But epsilon by 10 plus epsilon by pi sin pi by 10. This is the value. One can calculate what sin pi by 10 would be and divided it by pi. But I'm not doing it for the time sake. Now we are going to solve another problem. We are almost in the 2 hours, and now let me solve the another one. Last problem we have in our hand, and we can then stop our session. So this is the problem. You can understand this is another 1D problem. And last problem we have also a 1D problem, but a different extent. See, the question states that we normally think of a one-dimensional well as being horizontal. Suppose it is vertical. So what we usually do, we think that this is our power 0 to L. This is our V is 0 here, V is infinity at the walls. This is our general horizontal particle in the box. So what in this problem they are stating that now consider this is your box to be vertical. Okay, your x direction is here. It is your potential is actually we have to see it is 0 or not. I should not write it like that. Now see particle, then the potential energy of the particle depends on x because the presence of the gravitational field, right, which is mgh, right. Calculate the first order correction to the 0 point energy and evaluate it for an electron in a box on the surface of earth. Account for the result. Hint, the energy of the particle depends as height as mgh, where g is this. G is so small, the energy correction is also small, but it would be significant if the box are near to a massive star. Means G would have been. So here your perturbation, what they are saying is here this potential mgx. So gravitational field mgx due to this. So V was 0, but H1 is now they are saying as the box is like horizontal, vertical now, so it is acting as a gravitational field is acting as a you can say perturbation. So your obviously your first order perturbation to the ground state is going to be sin 0 mdx sin 0, right. Sin 0 is similar to by L sin n by x by L. So it is going to be mg is going to be outside, L is x to n pi x by l dx. Obviously this is a integration by parts. X cos 2n pi x by l dx. Then x cos 2n pi x by l. Okay, and the other part is going to be integration of d by dx of x. Then another integration cos 2n pi x by l dx. That lead to x l by 2n pi sin 2n pi x by l minus 1, and we obviously got this part from the earlier integration that it is going to be sin 2n pi x by l dx, right? X is 2n pi sin 2n pi x by l, and this is going to be l by 2n pi square minus minus plus cos 2n pi x by l. This is the part integration by parts we are going to get. So mg by l, it is going to be l square by 2 minus 0, and this part we are going to have xl by 2n pi sin 2n pi x by l plus l by 2n pi square cos 2n pi x by l to 0. So from this part, let us go to the next page, and we are going to get mg by l square by 2 from the first part obviously, and then here if we put l here, then it is going to become l square by 2n pi sin 2n pi, but with a minus here. So l square by 2n pi sin 2n pi also, and we know that sin 2n pi is obviously going to be 0 anyway, so that is 0. Then we have minus minus of minus here, l square 2n pi cos 2n pi minus of minus l by 2n pi square cos 2n pi, which is obviously going to be 1 because it is an even number. 2n is going to be even number, so that is that. And what about the containing 0? So if we put 0 in place of x, so this whole in term is going to be 0, and cos 0 from this side is going to be cos 0, that is 1. So, and already a minus is there, so minus minus plus plus l by 2n pi square cos 0. Cos 0 is 1. Let us see what are the terms we are left with. We have mg by l square by 2. This part is 0. We have l by 2n pi square from this third part, and we have l by 2n pi from this part, but the signs are different, so they are also going to cancel out. So we are only left with this, and that lead to mgl half mgl. So that is your our perturbation to the nth state is going to be so it wanted to calculate the first order correction to the 0 point energy. So now we have done to the nth. So this is the a first order correction to the nth state, the energy of the nth state. Now the first order and you can see it is independent of n, so obviously this is also the first order correction to 0 point energy. 0 point energy means the energy of the ground state, right? So half mgl is going to be the same. And see these if you have to evaluate for an electron, then you see the mass of an electron is very very less, which is so for here you need to oh, so this was your first order correction, which is also half mgl what we are discussing. Now g is at the earth surface is 9.81, uh, the unit is gram per meter per second inverse, right? Acceleration. But see, the mass of an electron is what? 9.11 into 10 to the power minus 31 kilogram, right? So if one can calculate for and L is how much? The energy of the particle on the so we need to calculate for a box on the surface of the earth. So 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 that is going to be very very less. But now g is going to be very very high near a massive star. What the question asks us that see that g is going to be very very small, so the energy correction is small, but it would be significant if the box is near a massive star. So because the g is going to be very very high. I know for the last part, last bit of part, I have tried to end it quickly, but I hope you understood what we are trying to do in this question. So first, we have done some problems with particle in a box. Then we have done one question with a particle in a simple harmonic oscillator kind of problem. What we have done it a little differently, and then now in this problem, what we are doing, instead of a horizontal box we are thinking of a vertical box, and due to that the gravitational field is acting as a perturbation, and due to that what is going to be the first order correction to the energy states, to the energy in for the all nth states in a general expression. And we found out in the general expression itself there is no part of there is no connection to the n. So obviously the 0 point energy and all the energies are going to have the same energy correction, first order correction. So with that I hope we have covered a lot in terms of the numerical problem solving of the perturbation theory. I hope you got a very good idea of the what needed to be done, right? Because you need to have a strong basis on the integration and the trigonometric relationships, right? What we have done so far, and with that actually we are going to stop today's session. If you have any doubt, write in the comment box, or you can also upload to the write it to the discussion forum of the NPTEL session. One of the TAs, me or someone else, will try to answer your queries. I hope this was a useful session, and the numericals. If you do this numerical by yourself, this will give you a boost to your confidence to solve the numerical problems in the exam. And I hope the session was useful. So with that, today we are going to end the session, and thank you for listening.